Here, I will discuss how to solve an axisymmetric heat conduction problem using ANSYS Mechanical. I'll assume that you have gone through the 2D conduction exercise in my online course, and this is an exercise from Module 1. And here I will discuss how you can extend the ideas that in that 2D conduction tutorial to axisymmetric heat conduction. If I go to the problem statement, it assumes that there's variation of the temperature only in the radial direction, and so it reduces it to a one-dimensional problem. Now, you cannot solve one-dimensional problems in ANSYS Mechanical, and probably because, in practice you hardly ever get one-dimensional problems, but you can solve 2D problems either in Cartesian or as axisymmetric using cylindrical coordinates. So let me go to my ANSYS model to explain how this is done. And this is actually my ANSYS result from 2D axisymmetric shown, as in 3D using symmetry. And you can see that there is temperature variation only in the radial direction. There's no temperature variation in the circumferential direction, and there's no temperature variation in the axial direction. And if I take a section through through that particular model, and I focus on this particular section, okay? And here you can see there's only variation in the radial direction. There's no variation in the axial direction, but we will have to have the axial direction also in there, but don't need to resolve it with any, with more than one division along here. We'll see that later. And once I know what's happening in this section, I know what's happening in any section. For instance, if I look at this section, this variation is the same as this. It's only flipped about the axis. And if I put in a cylindrical coordinate system, okay, let's say this is the origin, somewhere over here, and that's the radial direction, and that's the axial direction. I'll denote it as Z, as a lot of textbooks do. And so the temperature in this section is only a function of R and Z. In general, it can also be a function of theta, which is the circumferential direction, but we are assuming in the axisymmetric model that there's no variation in theta. And contrast this to, what we usually do, right? We say T is equal to Txyz, and there is no, in 2D, we assume there's no variation in Z. So this is analogous to that, but this is not the model you're using here. You're using the model here. And one thing to keep in mind is that ANSYS uses, it still says the horizontal coordinate is X. So once you switch to axisymmetric, you have to mentally substitute that the horizontal coordinate, even though it's called X, is radial, and the vertical coordinate is axial, even though ANSYS calls it Y. So you have to do that mental substitution. Which means that the geometry you give in ANSYS is just the rectangle. So if I go and highlight geometry here, see I just have that rectangle, and this distance is the inner radius, that distance is the outer radius, and that's the height. In the problem, you're given a length of 10 feet, but there's no variation along here, so I just assumed, I believe this is like 3 inches, and I changed units over here to inches. And so this height is arbitrary, and if you put in 10 feet, you're going to get a very long rectangle which make things awkward. So I would suggest cutting off the height to say about 3 inches. And also, since we are knocking off the dependence in theta, under properties, you have to make sure. So if I go to geometry properties, you have to make sure the analysis type is 2D, and you have to do this right at the start. Next, let's take a look at the governing equations and boundary conditions.